we can continue discussing aerodynamics. The second lecture of aerodynamics, introduction and principal definitions. Last time we talked about motivation to work in aerodynamics, to calculate and to make research on this area, why it's important, right? Principally because of need to determine forces and the reactions on the body. I think today we will already define which are the main purposes of aerodynamics. After we have some examples, it will be more clear. We have finished last time by definition on aerodynamic forces that appear on airfoil or any other aerodynamic body. This is a reaction force, and there could be also momentum created on the aerodynamic body, depend on which point we are using to observe. If you have some questions, please put in comments to this chat. Do not put just questions on theory. You can also ask things from work one. For people who already started to work on work one, would be useful to have some answers, I think. Well, so reaction force. This is the main force we have on aerodynamic body. Always could be split in a set of perpendicular forces, two perpendicular forces in case of the dimensional flow. These perpendicular forces could be L and D, lift and drag, sustentação e arrasto in Portuguese. These forces are directed vertically and horizontally, right? Lift force, which resists to weight, and drag force resists to thrust of the engine. If we make another split of forces according to the direction of an airfoil, we can see also two perpendicular forces, which are normal force and axial force. Normal force perpendicular to chord, and axial force is parallel to chord. Sum of two forces gives us reaction force. So we can make transition or transfer from normal and axial to lift and drag force, as we saw last time. I showed you how simply to calculate such transition using trigonometric relations. And I think it was simple. If not so much simple, please see another video where I show this question, an old video from previous semesters, or if still will be not clear, I could repeat one more time how transition from one set of forces could be done to another set of forces. Okay, these formulas of transition are here. I showed you last time how to obtain normal and axial forces from lift and drag. We also discussed, I showed you definitions of parameters used in calculation of aerodynamic forces based on pressure and shear stress. These parameters are infinite velocity, angle of attack between velocity and chord, leading edge, front edge of the airfoil, and trailing edge as final edge of the airfoil. Distance between them is called chord. Also, we see normally directed vector pressure to the normally directed to surface of the airfoil and tangentially directed shear stress vector. We see angle theta, which is angle between horizontal or vertical axis and shear stress or pressure, respectively. It's the same angle. Since pressure and shear stress have 90 degrees between these vectors, we have also same value of theta for these both cases. Theta characterizes for us direction of the body of the surface and is a geometrical characteristic, is not independent on flow, which is happening around this airfoil. We also saw that there is a lower distance starting from the leading edge and the upper distance starting from the leading edge. Lower and upper edges, they are not always equal. They can be same only for symmetric airfoil. Most of the airfoils are not symmetric, so upper and lower edges go differently, have different functions. And to denote parameters on upper and lower edges, we had subscript L or subscript U in pressure and also in shear stress. Okay, now how to calculate forces using this data previously defined. We can make it when we multiply area by pressure and area by shear stress, since pressure and shear stress are relative forces, force by one area, let's say Newton per square meter, for example, or kilogram per square meter, could be other units. Especially Anderson shows in his books many examples in imperial units, but because of these formulas do not change, they always preserve the idea of definition of force. Force is always area multiplied by relative force, independently on units. So based on this value, we can see, or based on this definition of force, we can see a model body or model surface shown on figure 119. This model surface has 1 meter in third dimension to simplify calculation. And in 2 x and y direction, we have some size on the airfoil, some length on the airfoil, which is denoted as ds. So the area of this element will be ds multiplied by 1. So simply ds is it will be area per 1 meter of airfoil, infinitely small. On this area ds, we can see pressure, which is normally directed, and we can see shear stress, which is tangentially directed to this area. Now, if we will try to calculate forces, you remember there are forces at least in 2 directions for bidimensional flow. We will multiply pressure by area. For example, calculating differential of normal force, first formula on the screen, we will use upper pressure PU multiplied by DSU multiplied by cosine of theta. Why this cosine of theta is representing to us direction. So we are basically using trigonometric function of cosine or sine of theta. We are calculating area of projection in normal direction, or in the other formula you can see sine of theta. We are calculating projection in the axial direction or direction of chord on the airfoil. Same we do not just with pressure, but same we do also with shear stress. Calculating force over this surface and multiplying by sine for normal direction of projection and cosine for the axial direction of projection of this force. These values you can see with negative signs, PU, because pressure is directed down, so it's going to negative direction of force, because we have defined origin of coordinates and direction of axis. P and tau is also directed down in this figure. Okay, upper part of axial force is also negative because it acts on the negative direction. Will be, if we split this function, we'll see negative value. And the tangential part, tau UDS, is with positive because it goes to positive direction of axis X. So these two formulas can be also repeated for the lower body, lower surface, DNL and DIL on the lower surface, and you will see these functions are very similar to functions for the upper surface. Just need to respect the sign, direction of force. When we need to calculate total force, we have to go from differential to integral form of this equation. So we are basically integrating upper and lower surface from leading edge to the trailing edge. We integrate components, normal component for upper direction, for upper side of the airfoil, and for the lower side of the airfoil, both pressure component and shear stress component for both cases. Same thing we do for the axial force. We have upper and lower source of axial force and pressure part and shear stress part. Once we receive these formulas, it's quite clear that normal and axial forces could be calculated based on this pressure distribution and the shear stress distribution along. Sorry, I have some sound here, cannot control this. This noise outside could be disturbing. After we have normal and axial force, we always can calculate lift and drag. Just need to use previously defined function of lift and drag. According to these two formulas, we can obtain, dependently on the value of angle of attack, these two forces. Is good to work in this way when normal and axial forces are first calculated, because normal and axial force are not dependent on angle of attack. And after just we had this N and A, we can, changing angle of attack, calculate, or introducing angle of attack, can calculate lift and drag forces. So this is the advantage of Formula 7 and 8, that they do not have angle of attack inside these formulas. They have only distribution of pressure, distribution of shear stress, and theta, which is geometrical characteristic of airfoil. Sign convention for this is for aerodynamic moments. Let's go to first calculate aerodynamic moments. I think, yeah. What is moment in our case? Moment is a product of distance by force. Normal force creates this moment, right? If we make this schematic here, for example, I have my normal force on my airfoil, and I choose any arbitrary point to calculate momentum. For example, the leading edge, I always will have distance, multiplying this distance between center of forces by my point of interest, I can calculate momentum. When we see another formula for axial force, which is staying on the chord, there is no such distance because this force goes through the axis, and there is no length to multiply. So momentum created by axial force is considered to be 0, and in most cases, let's see. At least this is a good simplification, very useful simplification to calculate momentum. In general, formula of momentum contains all the parts from previously calculated forces. Let's see which one. This part 1 is here, right? So it's a normal part of force generated by upper surface of the airfoil. This here we use, this is axial part of force, this one. Okay. As I told you, since force is applied close to the axis, right, or axial force is basically on the axis, this y coordinate in most cases will be equal to 0, and only x coordinate will contribute to significant value of moment. Same thing for the lower part of the airfoil. Just a moment, I will change color. I will show you this part of the lower part from normal component of the force is, I think, this one, right? And multiplied by x distance, and from the axial force is this part, okay? Also multiplied by y distance. For most of the airfoils, this will be significantly small value. So such a moment will be close to 0. In the most cases, we disconsider contribution of axial force to formation of global rotational momentum on the leading edge. Here you can see the subscript LE. It means that momentum is calculated on the leading edge of the airfoil. Okay, so we switch from force to momentum, just multiplying respected value of force by x or y coordinate. Please let me know if it's clear my explanation about formulas for forces and momentum, or something must be still explained. If no comments, I could continue. Sorry, my voice is not still recovered completely, so suffering a bit after 3 meetings. But okay, I can continue, I think.
It's okay so far.
Okay, thanks. Defined forces and defined moments. It should be something which should be not clear for you, but at least for me, it could not be clear. Look, it's very nice, these formulas, these relations. But when we are going to practical application, for example, I have my airfoil, I could calculate data distribution on the surface when I have geometry of my airfoil always taking derivate, I could calculate data at any point on the surface. So part of theta is not a problem in these equations, right? But there is another part which could be a problem, and this is pressure and especially shear stress. To calculate using these formulas, we need complete distribution of pressure and shear stress along the airfoil. That's the main problem, that probably before calculation of forces and the moments, we need to solve all the flow distribution, all the flow field around our airfoil and know exactly distribution of pressure and shear stress around the airfoil, or with analytical method, or with the numerical method, or experimental. So that's the problem. We have formulas, right? And we can use these formulas because geometry is known, but unfortunately, in most cases, must provide first a numerical simulation or experiments in order to get pressure and shear stress distribution. Okay, so I hope it's clear. We will go to those questions of pressure and shear stress distribution calculation further. So it's mainly one of the main purposes of aerodynamics to receive these parameters. Definition of aerodynamic coefficients is the next topic, very important. I hope will be clear for everyone. Aerodynamic coefficients, they are parameters, dimensionless, elaborated in order to unify all possible aerodynamic shapes, types of flow, and sizes, in order to bring some universal tool to compare different aerodynamic bodies with different conditions. So this is a tool which allows us to say which airfoil is better, one or the other airfoil, which airplane is better than the another airplane. These are purely aerodynamic definitions. They are not related to questions of design, structural strengths, fuel consumption, let's say, or other parameters, for example, related to green technologies. They are just purely deal with aerodynamic quantities. So they say from aerodynamic point of view, which structure is more efficient, which structure is better, which structure is worse, or which parameters this structure will need to have to be tested in another conditions, or which parameters the structure would have if we test it in other conditions, or which parameters of flow should be created if we would like to test a small-scale airplane inside aerodynamic tunnel. Also, these questions could be answered, and they are based on definition of aerodynamic coefficients. Aerodynamic coefficient is, there are several, and they are not something that is just given by nature. It's not like this. Aerodynamic coefficients were elaborated during many decades. There were many attempts to unify different aerodynamic bodies according to one or other criteria. And finally, they were established maybe 70, 80 years ago, not since the beginning of aerodynamics. First, aerodynamics as theory was elaborated where different schools, each school used its own criteria for comparison between different flows. And then finally, there was an agreement to use a specific criteria for all over the world scientific schools in order to have some uniformity in research or possibility to compare one or another aerodynamic structure. There are parameters which are called aerodynamic coefficients. There are several. Most of them are based on dimensionless force. Dimensionless force. It means that we are calculating parameter of force, dividing it by another force. There are lift coefficient, as you may see here, drag coefficient, normal force coefficient, axial force coefficient. They are all force coefficients, pure force coefficients. It means that to obtain such coefficient, we have to divide force, for example, lift force, by another characteristic force. In such case, it's this force is defined as dynamic pressure multiplied by area of the body. What is dynamic pressure? Dynamic pressure is 1/2 of density multiplied by velocity in square. Usually, this dynamic pressure is calculated for infinite conditions. Conditions which are way far from aerodynamic body, that body does not have influence on this condition. So it's long far from the body. For example, we are flying at 100 meters per second velocity. We know that far is 100 meters. We are flying, right? So on the far distance, we have this velocity. Near airfoil, near airplane, we have different velocity distribution. It's not exactly 100 meters per second, but it's different according to shape of the flow. So infinite conditions are important. The infinite conditions, they do not influence on this force. They are just, I'd say, serve as a reference to this force. So we have dynamic pressure, Q infinite, calculated. You know this from Bernoulli equation, right? Dynamic pressure. I hope you know. And we multiply by area. Which is this area? This area may be different for two-dimensional, for bidimensional, and for three-dimensional body. For example, for three-dimensional, as you may see from left upper image, is the plane area of the wing. This is the wing from above. We look on it, and we see the area of the wing. So this is the area we will use as a reference area for lift coefficient. For cylinder, for example, area is calculated as cross-sectional area of cylinder for three-dimensional. For bidimensional, this area is just equal to diameter or length of the body. For example, if we have some body with no diameter but just with length, we use as reference area length. For airfoil, which is some shape like this, we have one characteristic size, which is chord. So our characteristic area is chord. Why is not area? Because this wing can be extended to third dimension in 1 meter. 1 meter. So it's area. 1 meter wing multiplied by chord, we receive area of 1 meter wing. Using this as area in the formulas of lift coefficient, we obtain our aerodynamic coefficients. Aerodynamic coefficient can be for two-dimensional body, like airfoil, and can be for three-dimensional body, as wing, sphere, or complete airplane, or other. Any aerodynamic body may have its aerodynamic coefficient and a set of aerodynamic coefficients, not just one. Okay, so to obtain this force coefficient, we have to divide corresponding force by same absolutely reference force. Okay, pay attention that for all force coefficient in denominator, we use absolutely same reference force. Dynamic pressure multiplied by area, independently, bidimensional or three-dimensional, same. There is also another coefficient which is called momentum coefficient or moment coefficient, where we calculate Cm as ratio between two momentums, is moment which we have on our aerodynamic body, like for example, calculated by previous formula. Okay. Then we divide this moment by our reference force multiplied by the length. This length could be for airfoil is also chord, so we multiply by chord in square. So in this case, for momentum, we have C multiplied by C, okay, chord in square. For some aerodynamic bodies could be where we use length as reference size, we multiply by length, not by chord. In some aerodynamic body, for example, when we have sphere, it's just diameter, so we have diameter multiplied by diameter. For each type of aerodynamic body, we have an agreement, official agreement, which parameter is usually used or always used as reference size. It's always known. So please do not invent, if you do not know if it's chord must be used or diameter or length, you can always go to reference to, for example, site of NACA or reference book, and there is written which parameters used for reference calculation of aerodynamic coefficients. Another aerodynamic coefficient is called pressure coefficient. It's very interesting, this value. Pressure coefficient is also dimensionless. In this case, we divide pressure by pressure. We divide pressure difference actually between any point pressure where we would like to calculate pressure coefficient, for example, on the side of our cylinder. And we subtract ambient pressure, P infinite, which is constant, right? And we divide by Q infinite, which is dynamic constant pressure. Also, pressure coefficient says to us a lot of information. First of all, you have to remember that pressure on incompressible flow has always relation to velocity by Bernoulli equation, right? I will write it right here just for you to have reference. Is pressure plus density velocity in square divided by 2 will be same for any point you are choosing inside Bernoulli equation. So I type constant. constant. So if we use definition of pressure coefficient and Bernoulli equation, we will see following. Pressure coefficient with 0. What does it mean? It means that numerator of this ratio is 0 and the pressure is equal to infinite pressure. For us, when two pressure are equal, it means that velocity is same. Velocity does not change. So when Cp is 0, okay, I will write here Cp 0, it means that velocity at point where Cp is 0 equal to infinite velocity. So if you see distribution of pressure in distribution of pressure coefficient anywhere will be equal to 0, it means that at this specific point velocity reach infinite velocity. Then we see positive and negative value of pressure coefficient. Cp is positive more than 0. It means that difference of pressure is higher. So it means that P is higher. According to Bernoulli equation, velocity is smaller. So as a consequence, velocity will be smaller than V infinite. And reverse, when Cp is negative, it means that velocity at point where Cp is negative would be bigger than ambient velocity or infinite velocity. I think that did not appear yet on your screen. It takes some time. I don't know why. Maybe I will have to share again my screen. Just a moment. I will try to share again my screen because it delays. Just a moment. Sometimes we have these problems with Teams. There is no way to okay, I hope it will appear. In my computer already presenting, in yours. Okay, supposed to appear already. Please confirm if appeared.
Here is fine.
Okay, thanks. So pressure coefficient is an indicator, or not just of pressure by itself, but also of velocity. It says as velocity with respect to infinite velocity. If it's 0, then velocity is exactly infinite velocity. Positive, it means we reduce the velocity, have reduced velocity, and negative, we have increased velocity with respect to infinite conditions. And the last, but not least, and not the final, actually these coefficients did not finish yet here, but is these all coefficients which Anderson present in this book is the friction coefficient. Skin friction coefficient is the ratio between shear stress and dynamic pressure, giving us idea about ratio of friction force and velocity force. Okay. Anderson is giving to us one example, which I think is quite useful, very useful to as a demonstration to calculate distribution and values of axial force and axial force coefficient. Here he gives an example of wedge with the shock wave. It's not exactly a case of incompressible flow, it's completely compressible flow with shock wave. But this kind of flow has an advantage that inside compressible flow with the shock wave of such geometry, pressure is distributed uniformly on the surface of the wedge. This doesn't happen in the same way for incompressible or subsonic flow. This happens for supersonic flow quite typically. So what is given as input for this task is distribution of pressure on the surface. You can see it, pressure distribution shown on the diagram on the right side, and also giving the shear stress function is shown on the right lower side. And is asked as output to calculate axial force and to calculate axial force coefficient. This axial force coefficient is application of definition of axial force. This equation here did not appear yet on your screen, sorry. Is application of axial force coefficient formula to equation 1.8. So it corresponds to equation 116 in the book. Okay, so I hope it's clear. You can see how it's obtained. Actually, Anderson is giving task for students. If you understood how forces are calculated through integration of pressure, you could obtain manually as a homework, as part of the homework, axial force coefficient. Is not so difficult, just some mathematical transformations. So instead of using pressure and shear stress values, we use pressure and friction coefficients. Still have some delay today in demonstration of screen, very strange. Supposed to be faster, now it has some delays. Sorry for delays, but I hope it's more or less clear. How is obtained the solution? We have surface which is linear, so instead of integration of pressure, we just can use a product of pressure by size of the wedge on this upper side and lower side. Okay, we see that this size of upper and lower edge multiplied by sine of theta here is giving us just a value of projection. This one, blue one, I'm drawing here on the side. So it's the projection area. And multiplying projection by pressure, we obtain axial force. There is also another projection. There is also another back pressure, so-called back pressure P infinite, which acts on the end of the wedge. Also, it must be subtracted from the equation for axial force because it's directed against the flow. So it will be basically Pu minus P infinite. Right here, Pu minus P infinite, and we multiply by sine of theta and multiply by the F. Should be given somewhere in meter, 2 meters, right? 2 meters. So it's not sine, it's tangent of. So I will remove because it's not given the length, but is given, let's say, chord. So I hope it's correct. Tangent of theta multiplied by 2 meters. So this is contribution of pressure into axial force. We are basically written this part and this part. And probably should be also multiplied by 2 because we have upper and lower sides. So if I'm not wrong, it's supposed to be also multiplied by 2. And if we are trying to integrate the shear stress part, which I mark by red color, we need to take this integral because it's a function of a distance is changing. So we need to integrate from 1 to 2 meters and multiplying by cosine of theta because no need to multiply. Also need to do projection. Projection to axial direction. When we make it, usually I did it in class with my students, at least in mathematics, in numerical software, it takes this integral quite easily. We saw one consequence on here. Is not, there are no numbers, but okay. We saw the following consequence that part in blue, which corresponds to pressure force, is significantly higher than part in red, which corresponds to shear stress force. And this typically always like this for supersonic conditions, supersonic flow conditions. Usually viscous forces are much lower and pressure forces are much higher in case of shock waves. It means that for supersonic flows, in many cases, we can disconsider influence of viscosity and we can neglect contribution to aerodynamic forces. Viscosity part, it simplifies a lot the model. So we basically calculating just pressure part, obtain already huge part, maybe 80–90% of total force. In many cases, as preliminary estimation, this is enough for preliminary calculations. So it's one trick that we must always analyze and see which forces are more significant. If pressure force would be much bigger than shear stress force, probably it's a good strategy to consider just pressure force as a main source for aerodynamic forces, because shear stress is not that simple to calculate, need some integration, okay, need some additional data, and probably this additional calculation would take several times more time than pressure calculation, and will give you just 5–10% more accurate result, which is very small. So be careful when you are working with aerodynamic analysis. One of the first steps to do is to determine which parameters, which processes and sources are having more influence to the result and which could be discarded, disconsidered. Okay. Extremely important, Anderson shows this inside example 1.1, comparing these two forces. I think differences in order of 10%. So calculating this complex integral, you get just 10% gain, where 90% correspond to just pressure impact, which can be calculated very, very simple according to the equation I wrote you, analytical. Okay, just a moment. Center of pressure. Center of pressure is the point where we have action only of forces and we do not have action of momentum. So it's some point at which momentum does not exist, right? There is always on aerodynamic body, any type of aerodynamic body, there is some specific point which has only forces applied on its reaction force, actually one force reaction that could be split in two directions, could be split in direction of normal and axial, or could be split in any other set of forces which could be more useful for solution of one or another task. Momentum on the leading edge and center of pressure are related one with another. By formula you can see on the screen. Center of pressure could be calculated by known momentum on the leading edge divided by normal force, right? Or vice versa, momentum on the leading edge could be calculated when you know center of pressure and normal force. That's simple. Axial force is not present here because is aligned with chord, so it stays on the same line of chord and does not produce any contribution to momentum. So just normal force is contributing to momentum. In generally, as I told you, in almost all cases, you can consider like this. Here we see also one sign like this, prime here, prime. It means that force is calculated by 1 unit of length of the wing. So it's by 1 meter. It's a relative force. So it's Newton per meter of length of the wing, because in the third dimension we might have this wing of 1 meter. So I hope it will be clear why this prime appears in some formulas and some other formulas does not appear. Usually when we have m and n without prime, it means that we are talking or about two-dimensional body or about three-dimensional body as a whole. But when we have prime, usually we consider just 1 meter in third dimension. This could be clear. Another thing is, I did not talk before, I forgot a bit, but now I remember. When we have aerodynamic coefficients, let's go a bit back. These aerodynamic coefficients, they are defined for two-dimensional and three-dimensional bodies. How to understand if it's for two or for three-dimensional? For two-dimensional bodies is written in small letters, for example, CL, okay, CL, where for three-dimensional is already like this, is capital letter. Same for other aerodynamic coefficients. So capital letter usually is for three-dimensional body, and small letters are usually for two-dimensional body. Another comment about pressure coefficient. Pressure coefficient is a function of pressure. So since pressure is distributed along the airfoil for each point on the airfoil, pressure coefficient is different. Sometimes when you do work one, students deliver pressure coefficient just as one value for airfoil. So it's not correct. If you work with pressure coefficient, is a function, it's a distribution along profile of the airfoil. It's not just parameter, it's not just value for the airfoil. Where all other coefficients like lift coefficient, drag coefficient, momentum coefficient, they are just one value for the complete airfoil, for some angle of attack. For some specific angle of attack is just one value. But pressure coefficient and skin friction coefficient also are functions distributed along the airfoil, it must be really clear. If you see some data in internet and you see, oh, CP, one value for the airfoil, there is no distribution, there is just one CP. You have table, just one CP is okay. How much could be? 1, for example. CP is equal 1. What does it mean? It's not pressure coefficient, because sometimes you have center of pressure as CP. So please do not confuse center of pressure and pressure coefficient. Center of pressure is coordinate where we have just forces and do not have moment. And CP is pressure coefficient. XCP and CP. Okay, it could be a bit of confusion, but I hope you understand the difference and will be no problem in future. I just must say this for you. Different momentums, different points could be calculated when we know normal force and from previous calculation momentum on the leading edge. This normal force and lift force, in some cases, the same force. When angle of attack is equal 0, we have lift equal to normal force. Momentum can be calculated also for some specific points inside the airfoil, not just leading edge, but for example, for 1/4 chord, where we have coordinate on the airfoil exactly 25% of chord. At this point, usually can be fixed airfoil and can be generated momentum. This 1/4 chord is very typical point to connect airfoil on the test bench inside aerodynamic tunnel. The test section usually is connected at this point. So MC divided by 4 is momentum generated at 1/4 chord of the airfoil, and it can be calculated when you know lift and XCP. According to this formula, can be calculated momentum at 1/4 chord. You just take this value and put here, right? And M at 1/4 you can obtain. You can see it can be positive or negative, depends on relation between XCP and C divided by 4. Depends on what will be bigger. If XCP will be bigger, momentum will be negative. And if C divided by 4 will be bigger, momentum will be positive. Momentum can be positive or negative. It's absolutely not a problem, depend on shape of your aerodynamic body and depend on angle of attack, as we will see in future. Theory of airfoil says about these parameters. Okay, a big thing, dimensional analysis. I would like to make very small break. I would like to see if you have some questions, if you would like to talk something specific about what we already discussed. Let me know, and if no questions, in 1 minute we could continue. I just need a small break for my voice to recover. 1 minute and we talk about dimensional analysis.
Okay.
Okay, so had 1 minute break, and we can continue. There is a question in the chat: what is the difference between the moment in 1/4 of the chord and the other parts? The difference is the value, because more far from center of pressure, more different will be momentum, positive or in negative way. It's just the value of momentum. At center of pressure, it's 0. So, but when we have distance between center of pressure and point where we are calculating momentum, proportionally we are increasing this momentum linearly, right? Just lift force stays same, or normal force stays same, and we just change x distance between center of pressure and point of our interest. Usually airfoil is fixed also on the, not just on 1/4 chord, but also on the leading edge. Also another characteristic point where airfoil could be fixed. And at this point probably will have the biggest value of moment, or momentum coefficient, same. In the other direction, from CP to trailing edge, in this direction usually is not calculated momentum, because there is no application that allows to fix airfoil in point between center of pressure and trailing edge. So this is not usually direction of interest. Usually we are interested to work in this distance from first part, first quarter, more or less, approximately first quarter of airfoil. Also, for many airfoils, as you will see, according to airfoil theory, center of pressure is located exactly at 1/4 chord. Is typical for symmetric airfoils. Analytically, is shown that all symmetric airfoils have center of pressure at 1/4 chord. It's not 100%, like there is a margin. There is a margin, because the theory of airfoils deals with perfect flow with no boundary layer, for example. There is no theory which analytically describes and solves boundary layer equation around airfoils. So when we deal with the models of flows, in such case, is just pressure distribution is analyzed. Okay, I hope it was clear. There is another question. Is the moment at 1/4 constant with respect to different angles of attack? Maybe, maybe not. Depend on geometry and type of flow. 2 parameters will influence, actually 3, will influence Reynolds number, will influence Mach number, and will influence angle of attack. But of course, shape enters inside this calculation, but shape is usually constant for different conditions of the flow. So shape is there. As I told you, for only for symmetric airfoils is proven that momentum is 0 at 1/4 chord. For others can be observed different results. So Buckingham Pi Theorem, why? What is it? I think you already studied this somewhere, I hope. But just to remind you that this theorem allows to analyze more influencing parameters on aerodynamic body from aerodynamic point of view and see which actually criteria we need to use to understand which parameters influence on aerodynamic forces and which parameters influence on aerodynamic coefficients, which are more important than forces. Force can be different for different size of aerodynamic body, but aerodynamic coefficient is something that is unique for complete, for, let's say, similar bodies of the same shape for a set independently on the size. So Anderson makes a suggestion or assumption that the following processes influence on aerodynamic forces, and it's true, which is density, changing of density. Influence is the first parameter here in the relation R. We have influence of density. So depending on, for example, how high we are flying, altitude, changing density, changing the forces. Of course, it's obvious because more gas you have, more forces you will obtain. Less mass of gas you have with smaller density, smaller is the force. Quite obvious. Same with respect to velocity of the flight velocity. Faster, bigger forces, slower, smaller forces. Definitely there is a relation between velocity and force. We do not say now how will change linearly or will be some function, some complex function. Definitely is something that is not simple, right? Because flow is non-linear process. Any type of flow around body of arbitrary shape is very complex. So we cannot say, okay, we increase velocity 2 times, we'll have 2 times more force. It's not like this. It's not so linear. In some cases can be linear, but in general, not. Then C, size of the body or hoard in general. Influence, yes, bigger airplane, it means can carry more weight, can generate more lift. Quite obvious that size depends on the value of generated forces. Then viscosity, influence, of course, mu is I think it's dynamic viscosity, has its influence because depend on which fluid we are using, force will be different. And compressibility, A. As characteristic of compressibility is the speed of sound in meters per second. You already know that compressibility is calculated from previous courses. Probably you know that for Mach number smaller than 0.3, flow is incompressible. For Mach number higher than 0.3, flow is considered as compressible. Why exactly this? We discover on first or second week of gas dynamics. Now is not so much important. So speed of sound is characteristic of compressibility. Anderson says this. We agree, right? There are some proofs that speed of sound should be used as characteristic of compressibility. So if we are making such kind of functional analysis, we usually would like to see reaction force as a function of these 5 parameters, as I told you. And since this function can be defined, even though could be very complex function, we can find another function g. Just subtracting r, for example, we can have this function equal to 0. For Buckingham Pi Theorem, this g function is the most important base function. We just take r function, subtract r, receive 0. This will be function to analyze. You know, usually mathematics likes to work with the function that is having 0 at one side, on the right side, then is okay. We can compare. We can have a balance of quantities. For example, here we have a balance of forces. On the left side will be some force which is balanced with reaction force. Force created by these physical parameters as density, velocity, Horde, viscosity, and speed of sound will be balanced with reaction force. Buckingham Pi Theorem is a mathematical construct that says that the number of parameters that influence on your system will be a difference between physical parameters you are found that influence minus number of dimensional parameters like mass, length, and time. We have three parameters, three-dimensional parameters: mass, length, and time. And we have five parameters here that we found to be that are influencing on the reaction force. So totally, we have 5 minus 3. We receive 2. We receive 2 parameters. And in the book, I will not go deep because usually it's not difficult. No, absolutely not difficult. But I could keep this for your homework. You study Buckingham Pi Theorem and see how from these 5 parameters we can obtain just 2 parameters: Reynolds and Mach number. Reynolds and Mach number, subtracting, right, analyzing the dimensions of each of influencing parameters and making some system, very simple system of equations. We reduce 5 parameters or dimensional parameters and obtain 2-dimensionless parameters, Reynolds and Mach number. Usually I gave it, but when I ask after in exam, very few people answer this question. So I would like to give as a facultative point study of question of obtaining transformation from left side to right side. And as the final answer, I'm telling you the following, that Anderson proves using Buckingham Pi Theorem that any aerodynamic force coefficient is a function of 3 parameters, 3 independent, absolutely independent parameters: angle of attack, Mach number, and Reynolds number. This is mathematically proven. If someone of you will be interested to study, I'm ready to help, because there is nothing of complicated for me to help with this theorem to understand, right? But I do not think it's something that everyone must remember when he wakes up at night. It's for a few people. Here on this slide, I show idea that Anderson explains, that we create 3 independent functions, P1, P2, and P3, in its corresponding powers, each of parameters that we cited before enter, and using some mathematical algorithm, very simple technique, we find each of these unknown powers. It's quite simple, but no need to spend time. And as a result, we receive as a first influencing function Reynolds number. This one is Reynolds, right? No, it's not Reynolds. Sorry, is aerodynamic coefficient. Aerodynamic coefficient, CR, could be. As the second one is Reynolds number. And as the third one is what? Mach number. In details you study at home. It could be your part of your homework if someone will do. And then would like to discuss next time, please, you are welcome. We could talk. So Based on this Buckingham Pi Theorem, which concludes that any aerodynamic coefficient is just function of 3 independent parameters, which are also dimensionless criteria. Okay, alpha is outside, but there is no dimensional criteria for alpha. It's just alpha, nothing more, nothing less, just angle. Based on this idea, we see that any parameter which is not related to size or to force is a function of other parameters which are also independent on size, force, velocities, and center. Right? Because Reynolds number and Mach number, they are dimensionless. They could exist for a variety of conditions. And based on this equation, based on this theory, we define similar flows. What are the similar flows? Dynamically similar flows are when for two different flows, stream patterns or streamline patterns are similar. If they go streamlines, you remember what this is, a line showing how the flow moves. If streamlines are same, right, then second item is velocity profiles are same, if pressure profiles are same, temperature, and other parameters we can invent are same, plotted against common non-dimensional coordinates. So if we make a scaling, basically if we make scaling of both pictures, and we see that those pictures are same for velocity distribution, pressure distribution, temperature distribution, and force coefficients are same, so flows are similar. Also dynamically similar. Dynamically similar, that it means that they will have similarity with the transient process, inside transient process, also not just in stationary picture. And another way to check if the flows are dynamically similar from point of view of bodies. Two bodies are geometrically similar. For example, I have big airplane and small airplane, but both of these airplanes are same airplane but in different scale, or smaller airfoil and big airfoil just scaled. And we have similarity parameters same for both flows. Similarity parameters from previous slide, they are Reynolds number and the Mach number distributions. They are same. As an example, Anderson proposes this case here to prove that for bigger and smaller cylinder, we may have, well, we have similar flows. Okay, looks like patterns are similar, but we need to be sure. So we need to prove these three things. Shapes. It's simple, right? To see cylinder and cylinder. Okay, shape are similar. So item number one is satisfied. And second, similarity parameter, similarity criteria, Reynolds number and Mach number. So we can calculate these things. In this case, is need to use some assumptions that is saying to us that speed of sound is proportional to square root of temperature. This assumption will be proven in gas dynamics, and we will receive formula for speed of sound if you do not know yet. So it will be also known there. And based on this, we can prove that Reynolds 1 will be equal to Reynolds 2, case 1 and case 2, and Mach 1 will be equal to Mach 2. Once we prove it, we are okay. So let's see what we can do. Let's see what we can do. Also, the viscosity coefficient is proportional to square root of temperature. Also, this assumption, I think, Anderson has. Just one moment. I would like to confirm if it's true. Because if not, could be a problem. Yeah, it's true. So what we do? We calculate Reynolds and Mach number according to the function before. Would like to remind you that okay, we had formulas here. Mach number will be calculated as a ratio between velocity and the speed of sound. Updated between velocity and speed of sound, and Reynolds number will be calculated as density multiplied by velocity by diameter divided by viscosity. Okay. So let's see. Mach number is okay. Let me move a bit here so I could write easier. Mach number 1 is velocity 1 divided by A1 is proportional to velocity 1 divided by square root of temperature 1. Okay, and on the other side I will write Mach 2 is velocity 2 divided by A2, and then I will transform to relation this relation between case 1 and case 2. I will write that 2V1 divided by 2A1. This 2A1 because we have 4T1 and under square root it's 2. So I cancel 2 in numerator and denominator, and I will write equal to M1, same as we had in case 1. Same in terms of Reynolds number. Reynolds number 1 is density 1, velocity 1, viscosity coefficient is, okay, I will make proportionality here, not equal, square root of temperature 1, and divide, no, I think it's a bit different, right? No, viscosity is in denominator, of course. Here is just size, diameter, and here is square root of temperature 1. Okay, and the Reynolds 2 will be density 1 divided by 4. Then velocity 2 is 2 times 2 velocity 1. And then we have in denominator 2 square root of, for temperature 1, it's temperature 1 and multiplied by 2, like this. Oh, not equal, but proportional. And when we cancel all these values here, we see that it's same as Reynolds number 1. Reynolds 1. So I hope it is clearly shows that dimensional criteria are same for both flows, and geometries are similar. It means that both flows are similar. So Reynolds, Mach number same. Both are cylinders, similar flows. This is how we can test a different scale object, for example, in different conditions, and to receive similar flow distribution, and not just flow distribution, but also the forces and aerodynamic coefficients, same aerodynamic coefficients for both objects of different size. That's it. I would like to start next time from this moment because it's a nice starting point to refresh definition of flow similarity. I would like to see if there is some question to be answered today. If not, we could finish for today and continue next time. Please let me know if you have some questions. I'm expecting by voice or in chat. Could be in Portuguese, could be in English, absolutely no problem. If you ask in Portuguese, I will try to answer in Portuguese as well, if I know all the words for this answer. I think next time we already will have enough material or enough understanding of power of aerodynamics, and some questions that we discussed would be already creating some critical mass for us to formalize and to define main objectives of aerodynamics. It should be clear after we have this preliminary discussion about main objectives, because I decided to explain you first about some parameters, some details of aerodynamics, and only after present objectives of this big science. Okay, I see no questions. I think we could finish for today. Have a nice evening. And we meet on Thursday after tomorrow, continue introduction part of aerodynamics, and have a nice afternoon. See you next time. Thank you for participation today. Bye.